Okay, class, welcome back. I hope that you're staying safe and I hope that you're healthy. And I'm also hoping that the first week of online classes and activities have been successful for you. So these are the series of 3 videos. This will be the start of for the week of March 30th. Okay. Now, I know the last um, video we left off talking about Central Limit Theorem, and we're going to continue with that. But I think the last part of that video was talking about Bob and reaction time and so on and so forth. I'm going to interrupt that for a minute. We'll get back to that. But I wanted to use another example here just to show you how this might work. In this case, I'm doing IQ scores again, and we did this in class before everybody left campus. So with IQ scores, and I hope you can see this all right, the x-axis here, these are individual scores, okay? And IQ has a mean of 100 and a standard deviation of 15, okay? This is individual folks in this distribution. And so I want to do another z-score problem like we did before. I think that you're going to be comfortable with this, I hope. And I'm going to ask a question like, what percentage of the population has an IQ score above 110? So I've made the 110 right here, okay? And then the question I'm asking is, how many people or what percentage of the population is in this shaded area? So you should remember, I hope, that we can get that by using the z-score table, okay? And so here's our individual score of 100. No. Sorry about that, folks. Here's our individual score of 100. And if we calculate the z for that, remember z equals this individual score minus mu, and then divided by standard deviation. So it's 110 minus 100, that gives us 10 on top, and divided by 15, which gives us a z-score of 0.67, okay? This should be review for folks. This should be review, actually, okay? We're just finding the z-score for a particular individual score, in this case 110 minus 100, so it's 10 points away from 100. We're going to put that in terms of standard deviations, which is 15. So 10 over 15, we have a z-score of 0.67, 2/3 of one standard deviation away. Now I'm going to use my z-score table, and I'm just going to grab that for a minute. I'm going to use my z-score table like we've done before, and I'm going to look at, let's see, a z-score of 0.67, so the percentage in the tail is 25.14. So this here is 25.14%. So about 25% of individuals will have a z-score of 0.67, which corresponds to an IQ of 110. About 25% of the population has an IQ above 110. Okay? Now, here's the question, the new question. We're going to put that old information, and I hope that that was review. We're going to put that old information now with the new information that we have about Central Limit Theorem. We know that if we take out samples from this population, I mean, this is going to be like our bag of blocks, okay? If we take out samples, let's say in this case, we're going to do samples of n equals 6, okay? So what if we took out 6 people at a time and we calculated the average for that group of 6? Then we plotted it. Then we're going to take out another 6 people. We'll find out their average. We'll plot it. Take another group. We'll find out their average and plot it. Okay, everybody with me? We're just now going to do this from the population of individual IQ scores. And so we know that this distribution of sample means will have a smaller standard deviation, okay? The variability will come in. That's called regression to the mean. And so when we start plotting these means for samples, what we're going to see in this case is a distribution that looks something like this, okay? Relative to our distribution of individual scores, we have a distribution that has less variability, but we know that the mean for this distribution of sample means, we know that that's going to be equal to our mean for our original population. How do we know that? Because of the Central Limit Theorem. This happens, okay? It's just based on probabilities. And so we know that overall, when we do all of these sample means, right, and we're plotting these sample means, plotting the sample means, okay, we know that the variability is going to come in, regression to the mean, and it's going to, but it's going to still have a mean, that is the mean of all the sample means, is going to be equal to 100, right? So mu sub m is going to be equal to our original mu. That's the first part of the central limit theorem. Now we ask, well, what is the standard deviation for all of these sample means, right? What is the standard deviation for all of these sample means? Well, we know what that's going to look like because it's given by the central limit theorem. And that is the standard deviation for our sampling distribution of the means is going to be equal to the standard deviation from the original population divided by the square root of n, okay? So in this case, the original population standard deviation was 15. We're going to divide that by the square root of 6. And let me get my calculator, and you should do this too, of course. Where's my calculator? So, square root of 6 is 2.45. So 15 divided by 2.45. And so the new standard deviation of the sampling distribution of sample means for all samples of n equals 6, okay, is 15 divided by 2.45, so that ends up being 6.12, okay, 6.12. Central limit theorem, these are the two parts, okay? If you need to review the previous video, you can do that. Hopefully this is in your notes. It's certainly in the book, okay? And so this is what samples of 6, this is what samples, that is multiple samples of n equals 6 looks like. The distribution will have a mean of 100, standard deviation of 6.12, okay? So, now I have a new question, okay? Now I have a new question. It's analogous to the one I just asked about individual scores. I said, what is the probability that we're going to get an individual with an IQ score above 110? Hopefully that was easy. Hopefully that was review, right? We're just going to do a z-score here and then use the table, okay? I'm going to ask the analogous question for samples of 6. And here's the question. What is the probability that I would take out a sample of 6 people and their mean would be above 110, okay? So now I'm not talking about an X score of 110. I'm talking about a mean of 110. What's the probability that I'm going to randomly select 6 people from this population and their score is going to be, that is, the mean for the sample is going to be above 110, okay? Let's take a look. Now, this seems like it's kind of a standard z-score question. If I ask for individuals, I would just use this formula here, right? Standard z-score formula. In this case, I'm asking about the sample mean for a sample of 6. But let's take a look, okay? We're going to basically use the same formula, the same z-score formula that we used before. This is for individual scores. How does an individual score compare to the mean? We're going to put it in terms of standard deviation. Everybody with me? The z-score. Take the individual score, compare it to the mean, and divide it by standard deviation. That puts it in terms of standard deviations. Okay? In this case, we're going to use the same format, but in this, I made a mistake here. In this case, instead of an x value, I'm going to use an m, okay? So I'm going to compare the mean for the sample to the mean of all the sample means. Folks, just take your time, okay? I'm going to compare one sample mean, pull out a sample of 6. I'm going to compare that to what the mean for all the sample means look like. Divide by the standard deviation of the sampling distribution, okay? So here's what it looks like. Mean for my sample, 110, okay? I'm going to subtract 100. That is, I'm going to compare 110 to the overall mean of 100. Now I'm going to divide not by the standard deviation, but by the standard deviation of the sampling distribution, okay? So we've already calculated that. That's going to be 6.12. Okay? This is a z-score for looking at individuals. You can see that with the x. Okay. This is the z-score formula for samples. Sample mean, that should be an m. Okay. Sample mean compared to the overall mean for all the samples. Analogous, right? And then divided by the standard deviation for all the sample means. It's really the same formula. And sometimes, people get a little freaked out when I say it's the same formula. It just has different symbols. Well, we're comparing a position on the curve to the center of the curve, looking at variability. This is a mean on the distribution of all the means. We can pull this out. I'm going to have a blooper pretty soon here. Okay. Now we're just going to use the z-score formula, but have our distribution of sample means as our reference point. Okay? So, here we go. So here's our mean of 110 in this distribution of sample means. We know what the mean and the standard deviation look like, and so I'm going to calculate 110 minus 100 divided by 6.12. My z-score here now is 1.63. All right. Still 10 points away, but since our standard deviation is smaller, this 10 points away now corresponds to a z-score of 1.63. This 10 points away corresponds to a z-score of 0.67 because there was much more variability. Now, can you anticipate what the answer is going to be? So if I'm looking for a sample of 6, what's the probability that it's going to be greater than 110 versus an individual score with a score higher than 110? Because the variability in our sampling distribution comes inward, it's more difficult to find an extreme score in a sampling distribution. Okay? It's more difficult to find an extreme score because the variability is smaller here. Here, variability larger. So individual scores that are extreme are still not as probable as the mean, but they're out there. Okay? For a sample of 6 to have an average above 110, let's see what the probability is. The z-score is 1.63. Again, I'm going back to my z-score table. You need to be able to do this z-score table thing pretty comfortably. Once I have my z-score, so 1.63. The z-score, by the way, the table is in the back of your book, just to let you know. So you should bookmark that so you can go back and forth. So I'm looking at a z-score of 1.63, and so if I look in the tail, now there's only a 5.16% chance of getting a sample of 6 people with an average IQ of 110. Okay? So this is how we're going to put the z-score stuff. We've already done that. That was on the last exam, right? We can't just give that up now. We're able to do these probabilities and these percentages and proportions for individual scores. The only thing we've done here is we have made it useful in terms of samples. So in this case, my z-score is going to be the sample mean minus the mean for all the sample means, take your time, divided by the standard deviation for all the sample means. Okay? Really, same formula. Okay? Just have to keep in mind that we're looking at samples in this case. And we see that there's a lot less probability of getting a sample of 6 with an IQ average of 110, right? Take the sample of 6. I'm going to look at the average. What's the chance that it's going to be above 110? Only 5%, okay, 5.16. What's the chance of getting an individual with an IQ above 110? Much bigger, 25.14%, okay? Use the z-score table, and we can start answering these questions, okay? Where are we going to go next? Yeah. So this is an illustration that, again, like I was talking about LeBron James and basketball playing, it's harder to get a team average that's extreme, really good, or really bad. I mean, it's either extreme. It's harder to get a team with an extreme score than it is to get just an individual with an extreme score. Another way to look at this, we're going to look at this, well, let's do it. Let's do this. Let's see if we can do this example, okay? And it's going to be sort of the complement to this example. So let's do it. Let's do it. We're going to start again. We'll start with our standard IQ distribution. These are individual scores. These are individual scores. Okay. Mean for this distribution, the mean for this distribution of individual scores is 100. Okay. The standard deviation for individuals is 15. Everybody with me? Let's look at, again, samples. Of n equals 6. If we're plotting samples, down here you're going to have m sample means. Okay, these are not mu's, these are m's. We know that this is going to be less variable, right? We know that the mean for this distribution of sample means is going to be 100. We know that this distribution will have a standard deviation of, what did we say that was? 6.12. Okay? I like to put this little arrow up that sort of shows me the way that I got from here to here was to pay attention to the Central Limit Theorem, right? The mean of my distribution of sample means is equal to mu. Standard deviation for my distribution of sample means. Standard deviation of the original divided by the square root of n. That's how I got to this, okay? Everybody with me? So let's do this problem. And I'm going to actually give you a couple minutes to do this problem, okay? Let's ask, what's the probability of falling within 5 points of the mean for individuals? And then what is the probability of falling within 5 points of the mean for a sample of 6? I'll repeat the question. What's the probability that we're going to fall within 5 points of the average with individual scores? What's the probability that we're going to fall within 5 points when we have samples of 6? I'm going to give you a couple minutes. I'm going to give you a couple minutes and see if you can't figure this out, okay? So first step first, what is the problem asking? Within 5 points. So that means an X score of 105, an X score of 95. Anything in between those is within 5 points, okay? And that's the first thing you have to realize to start this problem. And then I'm asking for this I'm asking for this area here, okay? Well, we can get that area. We can absolutely get that area, okay? First thing we have to do, calculate the z-score for each of these. So it would be 95 minus 100 over 15. So this would be a negative z-score of 0.33. Over here, it's the same distance. 105 minus 100 divided by 15. So this is going to be positive 0.33. So now we have our z-scores. And we can go to the table. Let me take a look. Oh, I got to get my book. Hold on. Hold on. Give you some time to catch up there, right? Okay, 0.33. So I'm going to look at the tail for 0.33. The tail for 0.33 is 37.07. So that means because it's symmetrical, it's 37.07 here. Are you with me? So I'm going to subtract those from 100. $25.86. So in here, 25.86%. So that's my answer to the first question. Let's remind ourselves what the first question was, right? What is the probability that you're going to find an individual that has an IQ score within 5 points of the mean? Okay? The probability that we're going to find an individual within 5 points of the mean is 25.86%. Now, let's think this through a little bit. Second part of the question here, what's the probability that we would get a sample of 6 whose average is within 5 points of the average for all the samples? Let me say that again. What would be the probability that we would get a sample of 6 people that would be within 5 points of the average for all the samples of 6? Well, here's what we're going to do. We're going to look at all samples of 6. All samples of 6. Here's what it looks like. Here's what it looks like. Okay? So what I want to know is, what is the probability that we're going to be between a mean now, a mean of 105, and a mean of 95. So same position on the curve, 5 points away from the average, okay? And once again, this is what I'm looking for here. Let's see if you're getting it. Do you think the probability of getting a sample of 6 close to the mean is going to be greater than 25.86, equal to 25.86, or less than 25.86? And it's not equal, okay? If the samples are tending to pile up more toward the center, that is relative to the individual scores, if the samples are scrunching up, they're getting closer to the mean, then we should see more people close to the mean, okay? Everybody with me? These are more spread out, fewer in the middle. If we start bunching those samples up, they start coming in, regression to the mean, then we expect to find more toward the center. So this is kind of the complement of what we just talked about. Fewer in the extremes for samples, fewer in the extremes, more in the middle, okay, relative to this curve. So let's calculate it, all right? So here our z-score is the mean for our sample minus the mean for all of the samples divided by the standard deviation for all the samples. Pretty good. So that's 105 minus 100 divided by 6.12. Let's see what that is. I got my handy dandy cheap Staples $6.99 calculator. That's all I need. Just need something that I can get square roots, because later on we're going to be doing square roots. So let's do this. 105 minus 100 now divided by 6.12. So that z-score is 0.82. That z-score here is 0.82. Okay. And of course, it's going to be minus 0.82 here. It's symmetrical. I mean, we can do it. 95 minus 100 divided by 6.12. Okay. The first thing you got to do is get this number. We already got that. So let me go back to my z-score table. What is it? 0.82. 0.82. And once again, I'm going to get the tail for 0.82. 20.61. Okay. Now I'm going to take my entire graph. I'm going to cut off 20.61 and another 20.61. 58.78. 58.78%. Okay? 58.78% of the samples fall within 5 points. Okay? 58.78. If we compare that to individual scores, only 25.86 fall within 5 points of the mean. 58.78, very close to the mean, within 5 points, compared to 25.86. Okay? So, fewer samples in the extremes, more samples in the center when we start taking out samples. This is a sample of n equals 6. We can certainly take out samples of 10 or samples of 12 or whatever size sample that we want. And I want to show you now a schematic diagram because this is getting kind of messy. Okay, I'll show you a schematic diagram. Here we go. Okay, so here are two distributions, the dotted line and the solid line, of course. And I'm showing you that these are sample means on the x-axis. They both would have mu sub m if we took these samples from an original population. Here's a conceptual question. This is a good test question, by the way. I don't know if I'll remember to ask it, but we'll see. So dotted line versus solid line. Dotted line versus solid line. Which of these distributions do you think has a larger, represents larger samples? Larger samples, okay? Well, we know the larger the sample, the smaller the variability, okay? So this dotted line would be the larger sample, or from larger samples. this solid line from smaller samples. Remember that each of these distributions is a whole bunch of samples, 1,000, 10,000, whatever it is, okay? As the samples get larger, we see the variability gets smaller. That means those sample means are coming in. As the samples get larger, the sample means come in, okay? This mean will be equal to the mean of the distribution of individual scores. So I have a bag over here, right? And I'm taking out samples, plotting. Bag here, taking out samples, plotting. That's why I took so much time to go through that, because it's essential for you to remember what we're doing here. These are all sorts of sample means, okay? Listen carefully, okay? If I had a new bag, a new canvas bag, right? And I wanted you to guess what the sample mean for that bag was. Are you with me with the question? If I wanted to ask, if I had a new bag, all new blocks, okay? And I said, try to guess what the sample of that, what the mean of that bag looks like. I mean, this is called inferential statistics, right? This is inferential statistics. We are making guesses. If I wanted you to guess what the mean of those blocks in the bag look like, do you think you would have a better guess if you took out larger samples or if you took out smaller samples? Well, overall, if you took out larger samples will decrease the variability of my sampling distribution. If the mean for that distribution is equal to the original mean, this is the key, this is the key. Oh, this is so exciting. Well, for me it is. I'm trying to guess what's in that bag. If I take out a bigger sample, I'm likely to be closer to the mean than if I take out a smaller sample. I mean, let's just, for example, say that these are samples of n equal 10, okay? And these are samples of n equal 4. Well, overall, samples of 10 are going to be closer to my overall mean than samples of 4. So I want to have a larger sample to give myself a better guess about what's in that bag. And in fact, this value we know that this value is the standard deviation of the sampling distribution. It's the standard deviation of all the sample means. It's the standard deviation of all the sample means. But it does have another name, and it's a cool name. This is called the standard error of the means. It's the standard error of the means. Why is it called the standard error of the means? Well, listen, folks, inferential statistics means that you're making a guess, right? An inference. And when you make a guess, there's two possibilities. What are they? You can be right and you can be wrong, okay? Those are the two options. You can be right or you can be wrong when you make a guess. If I use a larger sample, those means are going to come closer to this. That's going to give me my guess for mu, okay? So it's called the standard error of the means. I want small standard error. I want a small chance of making an error, not a large chance, okay? The sample means will pile up closer to here with a large sample. If they're piling up here, then it's going to reduce my error. Okay? By the way, you guys are familiar with this if you pay attention at all to the news, because, let's see, what am I going to do here? Hold on one second. Let me get a new piece of paper. This is my drawing paper. So let's do this. So here we go. Hopefully you can see that. Can you see that? Let's do this. Okay. Sigma sub m is the standard deviation of the sampling distribution of sample means. And I underlined the S there because it's a whole bunch of means, right? Okay. Also called standard error of the means, because we're going to use the Central Limit Theorem to justify using larger samples to make guesses. Larger samples will make this value smaller. So larger samples gives me a better idea about what's going on in the distribution, gives me less error, okay? And this is abbreviated often as SEM, the standard error of the means. And I'll tell you, because I just said some of you are familiar with this, I mean a lot of you are familiar with this. If you read polls, political polls, they'll say, the president's approval rating is at 51%, or whatever it might be, okay? And then in the small print, it'll say plus or minus, plus or minus 3%. Or it might say plus or minus 1.5%, or it might say plus or minus 8%, whatever it is. That's actually the standard error of the mean, because when political pollsters are gathering this information, like I mentioned before, they're not going to ask 200 million people. They might ask 1,500 people. I mean, 1,500 is better than asking 200. And if you ask 1,800, it's better than 1,500. And 2,500 is better than 1,800. When I say better, listen, this has been a question on my exam. When I say better, I mean that this is smaller. Larger the sample, the closer I'm going to be to making the actual guess, okay? The larger the sample, those means are going to come in to the actual mean of the population, okay? But this is the standard error of the mean. You'll see that with all sorts of polling. That's what it means. Because they're making a guess, they want to indicate, I said the presidential approval rating is 51%. We'll do a plus and minus there. What these pollsters are acknowledging is, I'm going to say 51%, but it could be as high as 54, or it could be as low as 48. Okay? That's what the standard error of the mean represents. Okay? Before I end, let's go back to where I ended with the previous video. Oh, and hopefully this will be pretty good now. Wow, here we go. Okay, remember this? Normal reaction time. And I'm bringing in my weirdness. This is a question on your last exam. Statisticians are going to say, hey, anything in the extreme 5% is going to be considered weird. Okay? And we did a z-score for Bob's reaction time of 333. Let's do this. 333 minus 258. So he's 75 points away from the mean. If the standard deviation is 27, then Bob has a z-score of 2.77. So we're going to say Bob is weird. It's not really a value judgment. He's just so far out. It's improbable that we would see somebody like that from our normal distribution. But Bob said, hey, listen, you know, that reaction time of 333, I don't think represents my underlying population, what my reaction time really is. And so we say, okay, Bob, you can do 2 more trials. Let's see what you have there, okay? So we're going to collect Bob's data. Let's suppose that Bob's average, I'm going to put Bob's average for 3 trials. Let's say his average is, I'm trying to do some back calculation here, okay? Let's say his average is 280.00, okay? All right, what are we going to do with that? Well, we're going to take that average, we're going to compare it to what normal people look like when we let them do 3 trials. Normal people look like when they do 3 trials, okay? So what do they look like? Well, let's use Central Limit Theorem. They're going to have an average that's equal to the original average, but the standard deviation is going to be smaller. Central Limit Theorem. What is it going to be? The original standard deviation divided by the square root of n. So let's see, square root of 3 is 1.73. So we're going to do 27 divided by 1.73. So this new 15.61. Everybody with me? You should do this on your own. 27, that was the original standard deviation, right? Divided by the square root of 3, because we're doing 3 trials. So a sample of 3, okay? That gives us a new standard deviation for the sampling distribution, also known as the standard error. So I'm going to let you calculate Bob's new z-score. Let's see if he's abnormal, weird, or if he falls within the expected range. And that's where we'll start the next video. Stay safe, everyone. Hopefully it's not too crazy for you, and I hope your families are all in good health. Heed the precautions of healthcare professionals. And we'll see you on the next slide, or the next video, I mean.